Good afternoon, everybody. So it's my great pleasure to welcome Professor Jun Muk Hwang from the Institute for Basic Science in the Center of Complex Geometry. And he will talk about an award-winning paper, Frontiers of Science Award paper. And the title of this talk is on Hirschowitz's conjecture on the formal principle. Please welcome our speaker.
Thank you. Okay, thank you. As I already said yesterday, I'm very grateful for the internet, the ICBS and the committee for awarding me this prestigious prize. And the organizers asked me to explain the result of this paper, which was awarded. Although it's 5 years ago, 5 years old, so I try to explain the main result of this paper. This problem originated from Hirschowitz paper. So let me start with the basic definition, the basic setting. The setting is complex manifold X and complex submanifold A. And we consider the holomorphic normal bundle. And I'll denote by ON the zero section of the normal bundle. And we regard it as a submanifold of the complex manifold. I regard N as a complex manifold and this zero section as a submanifold, compact complex submanifold. So you have two compact complex submanifold, A in X and ON in N. Now this is a classical result from differential topology that there's a neighborhood of the compact complex submanifold which is diffeomorphic to some neighborhood of the zero section. This is not difficult to prove. In textbooks in differential topology you can find. And the main question we have is whether we can choose such neighborhood, which is not just C infinity diffeomorphic, but biholomorphic to the neighborhood of the zero section. That is the question. And it turns out that it's completely different from diffeomorphic case. So the answer is usually no. It's very rarely you have biholomorphic equivalence. Only in the exceptional case you have biholomorphic equivalence. So this justifies the following definition, germ of submanifold. So we say that two compact complex submanifold, A in X and A tilde in X tilde, have biholomorphic germs if there is a biholomorphic map between some neighborhoods of the two submanifolds. Then we say that they have biholomorphic germs. Now the problem is how to check this. You are given two submanifolds. This concept is natural from complex geometric point of view. Whether they have biholomorphic germs is a natural question. But how to check this? That's the problem. And in Grauert's paper, he mentioned question like this, uncalculable, because there's no way to, no algorithm to check this. So it's a very difficult question. So we'll try to find some easy way to check this. People try to find a more calculable method of checking this. And that's the concept of finite and formal neighborhood. So let's consider the ideal sheaf of the submanifold I. And then we define the infinitesimal neighborhood or finite neighborhood, finite order neighborhood. So when L is a positive integer, L's infinitesimal neighborhood of the submanifold, which we denote by the symbol, is a complex space the underlying complex space is just a compact complex manifold A, but its structure sheaf is this non-reduced sheaf with a nilpotent structure defined by L plus first power of the ideal sheaf. So this is L's infinitesimal neighborhood of A. And then the formal neighborhood of A is the inverse limit. Namely, we consider all of these infinitesimal neighborhood for any order. Then that's the concept of formal neighborhood. Now we say that two submanifold, A and A tilde, as a formal isomorphism of formal neighborhood. This means that you have isomorphism of this complex space, this infinitesimal neighborhood for arbitrary order, such that this collection of isomorphisms are compatible with respect to the obvious restriction map. Then we say that it is formally isomorphic. Now suppose two submanifold A in A tilde have biholomorphic germs. Then it's easy to see that they have isomorphic formal neighborhood. Because if you have a biholomorphic map between neighborhoods of A and A tilde, this neighborhood O and O tilde, biholomorphic map sending A to A tilde biholomorphically, then if you restrict this biholomorphism to the formal neighborhood, it gives formal isomorphism. Because in any finite order, it gives isomorphism between this finite order infinitesimal neighborhood, and they are all compatible. So biholomorphic germs give formal isomorphism of formal neighborhood. And so this is one necessary condition. For two submanifolds to have biholomorphic germs, one necessary condition is that they must have formally isomorphic formal neighborhood. So the natural question is, when is this the converse true? Suppose the two submanifolds have formally isomorphic formal neighborhood. Does it imply that they have biholomorphic germs? That is a natural question. And in Grauret's terms, a condition like this, formal isomorphism, is a calculable condition. You can, for example, when A is an algebraic variety, algebraic submanifold, then this condition is the algebraic condition. So it's something you can compute and check. So this problem is interesting because the biholomorphic germ problem is uncalculable, but this formal isomorphism problem is calculable, at least up to any order you can countably many conditions is a calculable condition. So this problem is people get interested in this problem for that reason, that they reduce an uncalculable problem to a calculable problem. So this is the motivation for this, the main definition. So this is the definition of a formal principle. Grauret introduced this concept. So the problem we are interested in is two compact submanifold having with the isomorphic formal neighborhoods. Do they have biholomorphic germs? That is the question we are interested in. And we like to make it more into a definition. So this is definition. We say that the formal principle holds for a compact complex submanifold A in complex manifold X, or equivalently, this compact submanifold in a complex manifold satisfies the formal principle if the answer to the above problem is yes. That is the definition. More precisely, for any other submanifold, so A in X satisfies the formal principle if for any other submanifold admitting a formal isomorphism, the two submanifolds have biholomorphic germs. Then we say that the formal principle holds. So it's just a convenient way to state this problem. Whether instead of asking this, we just ask whether a submanifold satisfies formal principle. So that is the main interest of our study. Yes, yes. First of all, normal bundle is determined by first order neighborhood. The first order neighborhood. So in a sense, the formal neighborhood is the extension of higher order normal bundle in some sense. Yes. Normal bundle is determined by just first order neighborhood. So that is the first step. Maybe it didn't explain. I mean, I will give another definition. Maybe this will help you. So formal principle for vector bundle. So what is this? This is the special case of formal principle, but W is a vector bundle on a compact complex manifold. Now we say that formal principle for vector bundle, the formal principle holds for the vector bundle, or the vector bundle W satisfies the formal principle if the zero section satisfies the formal principle as a submanifold. But there is no direct implication. Maybe this answers your question. There is no direct implication between the formal principle of a submanifold and formal principle for the vector bundle. It's related, it looks like related, but there's if A satisfies formal principle, it doesn't imply that the normal bundle satisfies formal principle. Neither the other way around. So they are somewhat related, but completely different problem. Okay, but this is, of course, this is one of the motivations. This special case of vector bundle is what many people are interested in, because this was precisely the difference between differential topology and complex geometry is reflected here. So this is special case is interesting. Now, the reason we define this formal principle is because it's not always true. So there's the counterexample, and this counterexample is constructed by Arnold. This is a line bundle of degree 0 on an elliptic curve that does not satisfy the formal principle. And as far as I know, up to now, essentially, this is essentially the only counterexample. So there are many counterexamples, but it's in some sense variation of Arnold example, all like this. In particular, there's no formal, no counterexample to formal principle when the submanifold is simply connected. So far, there's no counterexample. So this is essentially the only one. And the way Arnold discovered this is because he studied this divergent case of Poincare normal form of holomorphic vector fields. The classical small denominator problem. Yes, yes. So in celestial mechanics, this is what people discovered, that there are two germs of planar holomorphic vector field, V and W, at one point of C2, with formal isomorphism. So the two vector fields are conjugate on the formal isomorphism, formal isomorphism of neighborhood. But these two vector fields are not biholomorphic under any biholomorphic map. So this is what's called the small denominator problem. You have a formal equivalence, but the denominator is of the formal equivalence is smaller and smaller, so it diverges. And there's no way to find the convergent equivalence. So Arnold used this idea to construct this neighborhood of elliptic curve. But on the other hand, there are many cases where formal principle is known. So here are the cases where the formal principle is known. First, the negative normal bundle case. This is the origin of the problem, Grawet. When the submanifold can be contracted to a point, like a -1 curve, then formal principle holds. Actually, in this case, just the normal bundle determines the neighborhood. This is one of the exceptional case where the normal bundle determines the neighborhood of the manifold. And then there's a trivial normal bundle case due to Hirschowitz. So when the submanifold is a fiber over submergent, you have a smooth family of complex manifold, and this is just fiber. Then formal principle holds. Okay. Y is some modification of X, blow down of A. So Y is, sorry, I didn't explain it. Y is a contraction of X you contract this to some singular variety. 1 point. So this is Y. Thank you. And then there's also positive normal bundle case. One case is Commichaud and Grawet. When the normal bundle is ample and globally generated, then the formal principle holds. There's another case, Hirschowitz, when deformation of A having non-empty intersection is A inside X, cover neighborhood of A. So this is some geometric condition. Now, in all these cases, in all these known cases, the proof is essentially use the idea of Artin approximation theorem. The Artin approximation theorem is the following. When you are given an system of analytic equations for finitely many unknown functions in n variables near 1 point. Now, if the system has a formal solution, then this must have a convergent solution. That is Arnold, no, that's Artin's approximation theory. In particular, you can find a convergent solution which approximate the given formal solution up to any order you want. So that is Artin approximation theorem. This is, of course, if you look at the known cases, this is after Grawet result, 67. So, but the other cases use proof of these cases use Artin approximation theorem. Grawet is before Artin approximation theorem, and in a sense, Artin approximation theorem is motivated by Grawet theorem. He tried to generalize Grawet's argument to much more general case. And if you apply this in the Grawet situation, where the set is exceptional set and you can blow it down, if you just apply Artin approximation at this point, then you obtain Grawet result. Now the point is that this is a local result. It's a statement about germ of 1 point. So you cannot apply this to germ of a submanifold. And in the known cases of formal principle, the proof is somehow you reduce the formal principle to 1 point, to a statement about 1 point, and then apply Cartan approximation theory. That is how people prove it. So here's the rough sketch. So when the submanifold can be contracted to 1 point, the problem is localized to this neighborhood of the contracted point. It's a local problem. And when the submanifold is a fiber of a submersion, then the problem can be localized to the base point somehow, or the downstairs. So it's also a local question. On the other hand, when you have this positive normal bundle case, the result of Komisho-Grawitz and Hirschowitz, they actually proved a stronger result. They proved that the given formal equivalence actually converges. It's a much stronger result. And when you are interested in convergence of a given formal power series, it is already a local problem. Because you check the convergence at each point. It's already a local problem. So you can apply Cartan approximation theorem at each point. So in this way, all the known proofs somehow uses Cartan approximation at 1 point. And then Hirschowitz made the conjecture, which generalized both the trivial normal bundle case and positive normal bundle case. And Hirschowitz proposed the following conjecture, that if you have a submanifold, which is unobstructed, in the sense that the deformation space is smooth, and the normal bundle is globally generated, namely the global sections of normal bundle generate all fibers, then the formal principle holds for the submanifold. This was the conjecture. And this covers both trivial normal bundle case and positive normal bundle case. And one corollary of the conjecture is that a globally generated vector bundle on a compact complex manifold satisfies the formal principle. So this is one corollary. Now the main theorem of the paper, my paper is this theorem, that we assume that submanifold is unobstructed and normal bundle is globally generated. These are the same condition as in Hirschowitz conjecture. Now I make one more assumption, that the sections of the normal bundle separate points. In other words, if you have two different points on the submanifold A, then the sections of normal bundle vanishing at X and sections of normal bundle vanishing at Y are different. So there are some sections which vanish at X but does not vanish at Y. So that's the assumption, that it separates points. And then what we can prove is that under these conditions, a general deformation of A in X satisfies the formal principle. So I could not prove that all A satisfying this satisfy formal principle. But I can prove that a general deformation of such submanifold. No. The point is, I have absolutely no example of any manifold other than, as I say, other than Arnold's example. We do not have. Yeah. So on the any additional condition, we have no counterexample of formal principle. So I cannot give any example. Okay. So this is the paper which was awarded the award. There are some, although this may look more restrictive than Hirschowitz's original conjecture, there are some interesting corollaries. So W is a globally generated vector bundle on a compact complex manifold, and it separates points. Then it satisfies the formal principle. So for vector bundles, you don't need to deform. You don't need this statement about general deformation. Just zero section itself satisfies the formal principle already. Why? Because deformation of zero section are just global sections of vector bundle. And it's easy to see that the neighborhood of any global section is equivalent to have a biholomorphic germ, biholomorphically equivalent to neighborhood of zero section. So for vector bundle, it doesn't matter which section you choose. So by the main theorem, the formal principle holds for general sections of W, and then it implies that the formal principle holds for the zero section, because any two sections of a vector bundle have biholomorphic germs. That's one corollary. Yes. Yes. Yes, yes. No. Here is the point is that the statement of vector bundle is a special case of statement of submanifold, because this is for zero section. What I said between the case you mentioned is the case of submanifold and its normal bundle. Yes. But here W is already the normal bundle. If you consider vector bundle, then it's already normal bundle of the zero section. This is one corollary. Another corollary is that if you have a globally generated vector bundle on a Fano manifold, then it satisfies the formal principle. In this case, we justify the original Hirschowitz conjecture. We don't need to assume the separation of points in this case. Because it's a simple trick that for Fano manifold, you can enlarge the vector bundle by anti-canonical bundle to make a new vector bundle which have separation property. And then from this, you can deduce the formal principle for original bundle. So for Fano manifold, it has this special property that the anti-canonical bundle has lots of sections. And using this, you can remove the additional assumption about separation points. Yes. So for this direct sum vector bundle, satisfy the formal principle, but then you can deduce the formal principle for W from this direct sum vector bundle. Another theorem, another corollary is a rational curve. So this was actually my original motivation for the problem. Yes? Anti-canonical bundle. It's Fano. It's Fano. It's anti. Then I don't know how to deduce this. There's some difference between canonical and anti-canonical bundle. The problem is this formal principle is a non-linear problem. If you have two vector bundles satisfying formal principle, the direct sum need not, there's no reason why the direct sum satisfied. And for Fano manifold, somehow you can, I cannot explain the detail here, but for anti-canonical bundle, you can somehow deduce it. But for canonical bundle, I don't know how to do it. Thank you. So one of my original motivation is this special case. It's a rational curve with a normal bundle is semi-positive, globally generated. This is called a free rational curve. So my original motivation was whether a free rational curve satisfies formal principle. That was because it's related to my work with Naiming Mo about minimal rational curves, where we need the biholomorphic equivalence of such rational curves, and whether I can check it by formal neighborhood? That was the question. Actually, this was asked by, the question was asked by Osawa when I gave a talk about minimal rational curves. He asked this question, and that was the motivation for this work. This is the case I'm very interested in. And so as a corollary of the main theorem, a general deformation of a smooth pre-rational curve satisfies the formal principle. If the normal boundary is trivial, this is a special case of Hirschowitz result. If the normal boundary is non-trivial, then its global sections separate points, so it follows from main theorem. So these are the main corollaries. Okay, so now let me explain the idea behind the proof of the main theorem. Okay, the condition for the main theorem is that you have a submanifold, which is unobstructed, and the normal bundle is globally generated. This implies that you have a very nice universal family of deformations away. So you have a double fibration, what's called Duadi space, the universal deformation space of submanifold. So you have a double fibration. This rho is a universal family of such deformation, and mu is the evaluation map. So what you have is you have such a double fibration such that if you choose one point here, Z, and then this fiber here, it goes to AZ, submanifold in X. And this double fibration classify all deformation of such submanifold. And everything is very nice. All three are complex manifold. This is proper smooth, and this is submersive, and so on. These follow from this assumption, that unobstructed and globally generated. Now, the interesting thing is such universal deformation is functorial construction. So if you have a formal isomorphism, between submanifold here, if you have formal isomorphism, then it can be lifted. Any formal isomorphism can be lifted to a formal isomorphism between this universal family. That's what I wrote. If you have a formal isomorphism, you can lift it. Because the construction is functorial. And this formal isomorphism respects this double fibration, because everything is functorial. So it's not just arbitrary formal isomorphism of this neighborhood, but formal neighborhood, but they respect these two maps. So that is the important property. Now the key step of the main theorem is the following. Namely, we can extend this formal isomorphism at a general point somewhere here. If we choose a general point here, y, then corresponding point here, then what we want to do is that you can extend this formal isomorphism to a biholomorphic map between neighborhood. So that's the phi. This is what I like. You can extend this formal isomorphism in a neighborhood of this point y to a biholomorphic isomorphism, which respects rho and mu. So from this neighborhood of submanifold, I go to a neighborhood of one point. But instead of, so I lose information. I go to local situation. But instead, I require that this, what I want is that this biholomorphic map preserve these two double fibration. So this biholomorphic map is supposed to respect this double vibration and this double vibration. So instead of this global submanifold information, I go to local information, but I replace the global information by this double vibration information. So that's the point. So that's what I want, that I can go to biholomorphic map, from formal map to biholomorphic map locally, but I can, in such a way that they respect the double vibration. So that this is the key step. Once you have this key step, then you can descend. Once you have such biholomorphic map, you can descend it to biholomorphic map between here, because it respects the double vibration, it descends. And then you can do this, you can analytically continue this to a biholomorphic map between neighborhood of A and A tilde. You can do analytic continuation. And the reason I require, so you can do analytic continuation, but when you do analytic continuation, you encounter the multi-valuedness issue. It's usually not univalent, but this condition on separation of points by sections is precisely to exclude this possibility. So this somehow, this condition, separation of points, resolve the multi-valuedness issue. So you actually, once you have such biholomorphic map, then the analytic continuation becomes univalent, and you obtain biholomorphic map. So that's how you prove this. So the main issue is this key point, key step, is about, it's a local statement, whether you can obtain from formal equivalence, whether you can obtain biholomorphic equivalence, but respecting the two double fibrations. So roughly what we need is the Cartan approximation theory for differential equations. So to find this biholomorphic equivalence respecting double fibration, what we need is we need to solve a system of analytic partial differential equation. Because the requirement that it respects double fibration is a differential condition. It becomes, it's not just an analytic system of analytic equation, but there's a differentiation involved. So you obtain a system of partial differential equations. So what we want is something like Cartan approximation for PDEs. So for a system of analytic PDEs, for finitely many unknown functions in a germ of one point, suppose the system has a formal solution, then can we find the holomorphic solution which approximates the given formal solution to any order we want? Now, if this was not PDE, but just the analytic equation, then this is precisely Cartan approximation theory, which is true. But now we ask not just system of analytic equation, but system of analytic PDEs. That's the difference. And the answer is no. It's cannot be true. The reason is you have this divergent case of Poincare normal form of holonomic vector field. And that's exactly a problem like this. You are given two vector fields, and you want to find, you assume that there's a formal equivalence of formal conjugation of these two holomorphic vector fields. And we want whether there's a convergent solution, but this example of small denominator example, it is a counterexample to this local approximation for PDEs. So for system of PDEs, such approximation does not hold. We cannot use this kind of result to prove what we want. But there's a substitution for this. And this is what's called Cartan-Keller theorem with estimates. And the version I know of is due to Lagrange. And this is exactly the statement we want, but there's additional condition. So it's not just any system of analytic PDEs, but if you have an involutive system of analytic PDEs, then the approximation theorem holds. Namely, if you have an involutive system of analytic PDEs for finitely many unknown functions, germ at one point, if the system has a formal solution, then there is a convergent solution. Now the issue is, what is this condition, this involutivity? This is a rather complicated, very complicated algebraic property of the system of PDEs. Can be expressed in terms of smoothness of certain subschemes in J space. So it's a property of the system, algebraic property of the system, but usually very difficult to check, very complicated. But we want to apply this Lagrange theorem to a neighborhood here and find the convergent solution. Because we know that there's a formal solution of this system of PDE. And so what we need is to show that this system of PDE is involutive. That's what we need. Very fortunately, okay, so how do we know our system is involutive? Very fortunately, there is a general method. This is Cartan's prolongation method. What Cartan suggested heuristically is that any system of analytic PDEs become involutive at sufficiently general point outside some nowhere than subset after finitely many prolongation. So if you go to general points, then it becomes involutive. That's roughly what Cartan says. Prolongation means that you enlarge the system of PDEs by adding more PDEs, by taking differentiation. But this was not very precise. So later, many people, there are many versions of the precise version of the Cartan prolongation theorem. And then, the one we used was due to Morimoto. So, for the system of PDEs describing equivalence of G structures, this double fibration is a special case of G structures. So this kind of system, the involutivity was first proved by Singer and Sternberg, and then generalized by Tanaka, Ueno, and then the most generalized version is due to Morimoto, and we need this Morimoto version. So this is what is proved, is that a system of PDEs describing analytic equivalence of two holomorphic G structures becomes involutive after finitely many prolongation outside a nowhere than subset. So this guarantees that if you go to a general point, not a general fiber, a general point of the universal family, then you can solve the approximation theorem for PDEs. So this formal equivalence respecting the double fibration guarantees existence of biholomorphic equivalence respecting the double vibration if you choose these points sufficiently general. That's so in particular, the problem, the system of PDs describing the equivalence of double vibration becomes involutive at a general point. So we can apply this to a general point. And that's why I need the condition that not the submanifold itself, but sufficiently general deformation of the submanifold satisfy this condition. That's how we prove the result. Thank you very much.